Welcome, ladies and gentlemen, to an extraordinary journey into the fascinating world of general relativity. Today, we invite you to embark on a mind-expanding exploration of one of the most profound theories ever formulated in the realm of physics. In a universe where time and space intertwine, where massive celestial bodies shape the very fabric of reality, and where our understanding of gravity takes a mesmerizing leap forward, general relativity stands as a pinnacle of human achievement, forever changing our perception of the cosmos. It all began with a remarkable mind, Albert Einstein. Over a century ago, this brilliant physicist shattered the conventional wisdom, rewriting the laws of gravity and revealing a universe more awe-inspiring than we ever imagined. At the core of general relativity lies the concept of spacetime, a four-dimensional framework that seamlessly weaves together space and time. Within this dynamic stage, gravity emerges as the majestic conductor, orchestrating the dance of celestial bodies, shaping the paths they traverse, and even bending the very fabric of spacetime itself. Through general relativity, we delve into the enigmatic depths of black holes, where gravity becomes so intense that nothing, not even light, can escape. We witness the extraordinary phenomenon of gravitational waves, ripples in spacetime generated by cataclysmic cosmic events that propagate through the cosmos, carrying with them the echoes of the universe's most energetic moments. Join us as we journey alongside brilliant minds, physicists, astronomers, and cosmologists who continue to push the boundaries of knowledge, unraveling the mysteries of our universe through the lens of general relativity. Together, we explore the grandeur of space, the nature of time, and the profound implications of this groundbreaking theory. So, fasten your seatbelts and prepare to be captivated by the awe-inspiring concepts, mind-bending theories, and astounding discoveries that await you in our exploration of general relativity. Get ready to embark on an epic voyage, where reality unfolds in ways you never thought possible. General relativity is a theory of gravity that was developed by Albert Einstein in the early 20th century. It provides a description of gravity as a curvature of spacetime caused by the presence of matter and energy. In this theory, the motion of objects is not solely determined by forces acting on them, but also by the geometry of the spacetime in which they exist. To understand general relativity, let's break it down into several key concepts. Spacetime. In classical physics, space and time are considered separate entities. However, in general relativity, they are unified into a single four-dimensional continuum called spacetime. Spacetime is not a fixed background, but a flexible, dynamic structure that can be influenced by the distribution of matter and energy. Equivalence principle. The equivalence principle is a fundamental principle of general relativity. It states that the effects of gravity are indistinguishable from the effects of acceleration. This means that an observer in the gravitational field cannot differentiate between the force of gravity and the force experienced in an accelerated frame of reference. Curvature of spacetime. According to general relativity, the presence of matter and energy causes spacetime to curve. Imagine placing a heavy object, like a massive star, on a rubber sheet. The sheet will deform under the weight of the object, causing a curvature. Similarly, in general relativity, the mass and energy of objects curve the fabric of spacetime itself. Geodesics. In curved spacetime, the paths that objects follow are not straight lines but curves called geodesics. These geodesics are determined by the curvature of spacetime and represent the paths of least resistance or the natural motion of objects in the curved spacetime. Einstein field equations. The mathematical formulation of general relativity is represented by Einstein's field equations. These equations describe the relationship between the curvature of spacetime and the distribution of matter and energy within it. They can be written as R 1/2 Rg equals hgt, where R represents the curvature of spacetime, R is the scalar curvature, g is the metric tensor that encodes the geometry of spacetime, T is the stress energy tensor representing the distribution of matter and energy, and G is the gravitational constant. Gravitational waves. General relativity predicts the existence of gravitational waves. These are ripples in the fabric of spacetime that propagate outward from accelerating masses. Gravitational waves were detected for the first time in 2015, providing strong confirmation of Einstein's theory. Tests and confirmations. General relativity has been subjected to numerous experimental tests and observations, all of which have confirmed its predictions. These include the bending of light around massive objects, gravitational lensing, the precession of Mercury's orbit, the deflection of starlight by the Sun, and the time dilation effects near massive objects. General relativity is a complex and mathematically sophisticated theory, and the above explanation only scratches the surface of its intricacies. It has revolutionized our understanding of gravity, provided explanations for phenomena such as black holes and the expanding universe, and serves as the foundation for modern cosmology. The mathematics of general relativity involves the use of tensor calculus, which is a mathematical framework that allows us to describe the curvature of spacetime and the motion of particles within it. To fully understand the mathematics of general relativity, it's helpful to have a basic understanding of differential geometry, tensors, and the concept of manifolds. Manifolds. In general relativity, spacetime is described as a four-dimensional manifold. A manifold is a mathematical space that locally resembles Euclidean space, but can have a more complicated global structure. In the case of spacetime, it is a smooth manifold, meaning that it is continuous and differentiable. Metric tensor. The metric tensor is a fundamental object in general relativity that encodes the geometry of spacetime. It describes how distances and angles are measured in the manifold. In four-dimensional spacetime, the metric tensor is a symmetric, rank -2 tensor with 10 independent components. Curvature. The curvature of spacetime is determined by the distribution of matter and energy within it. It is described by the Riemann curvature tensor, which is a rank -4 tensor that characterizes the curvature at each point in spacetime. The Riemann curvature tensor has 256 independent components, but many of them are related by mathematical symmetries. Einstein field equations. The Einstein field equations relate the curvature of spacetime to the distribution of matter and energy. They can be written as R1/2 Rg equals hgt, where R represents the components of the Ricci curvature tensor, R is the scalar curvature, G is the components of the metric tensor, T is the components of the stress energy tensor, and G is the gravitational constant. These equations are a set of 10 coupled, nonlinear partial differential equations. Solving them is a highly complex task and often requires approximation techniques and numerical methods. Einstein's equation in covariant form. The Einstein field equations can also be expressed in a more compact and elegant form using tensor notation. This is known as the covariant form of Einstein's equation. R1 to Rg equals hgt, where R is the Ricci curvature tensor, R is the scalar curvature, G is the metric tensor, T is the stress energy tensor, and the indices and represent the four spacetime dimensions. Geodesic equation. The geodesic equation describes the motion of particles in curved spacetime. It is derived from the principle of least action and can be written as frac d2x d2 plus frac dx d frac dxd equals 0, where x represents the coordinates of the particle, is the proper time along the particle's world line, and are the Christoffel symbols of the second kind, which describe the connection between neighboring points in curved spacetime. Solving the equations of general relativity analytically for realistic situations is often extremely challenging due to their complexity. Therefore, various approximation methods are employed, such as perturbation theory, numerical simulations, and numerical relativity techniques. These methods allow scientists to study the behavior of gravitational systems, such as black holes and neutron stars, and make predictions about observable phenomena, including gravitational waves and the dynamics of the expanding universe. It's important to note that the mathematics of general relativity is a powerful theory that is used in various areas of physics and astronomy to explain and predict a wide range of phenomena. Here are some of the key applications and uses of general relativity. Gravitational effects. General relativity provides a more accurate description of gravity compared to Newton's theory of gravity. It explains the observed phenomena such as the bending of light around massive objects, gravitational lensing, and the precession of planetary orbits, such as Mercury's orbit, more accurately. General relativity also predicts the existence of gravitational waves, which are ripples in the fabric of spacetime caused by accelerating masses. The detection of gravitational waves in 2015 confirmed this prediction and opened up a new window for studying astrophysical events like merging black holes and neutron stars. Black holes. General relativity plays a crucial role in the study of black holes. It predicts the existence of event horizons, which are boundaries beyond which nothing, not even light, can escape the gravitational pull of a black hole. The theory also describes the properties of black holes, such as their mass, spin, and the distortion of spacetime near the event horizon. General relativity provides the mathematical framework for understanding the dynamics and behavior of black holes, including the accretion of matter onto them and the emission of Hawking radiation. Cosmology. General relativity forms the basis of modern cosmology, the study of the universe as a whole. It provides the framework for modeling the large-scale structure and evolution of the universe. By incorporating the principles of general relativity, cosmologists can explain phenomena such as the expansion of the universe, the cosmic microwave background radiation, and the formation of galaxies and galaxy clusters. General relativity also plays a crucial role in theories of cosmic inflation and the early universe. GPS and time dilation. General relativity accounts for the effects of gravitational time dilation. Clocks in the gravitational field run slower compared to clocks in regions of weaker gravity. This effect is critical for precise navigation using the Global Positioning System, GPS. The satellites in the GPS network are affected by the Earth's gravitational field, and the timing adjustments based on general relativity are necessary to ensure accurate positioning. Fundamental physics. General relativity is an essential tool for studying fundamental physics and exploring the frontiers of theoretical physics. It is often employed in conjunction with quantum field theory in attempts to formulate a theory of quantum gravity, which aims to unify general relativity with quantum mechanics. Such a theory would provide a consistent framework for describing the behavior of matter in spacetime at extremely small scales and under extreme conditions. The applications of general relativity extend beyond these examples, as it has implications in fields such as astrophysics, gravitational lensing, gravitational waves, and high-energy physics. The theory continues to inspire new research, uncover novel phenomena, and deepen our understanding of the fundamental workings of the universe. Goodbye.